In this video, we'll explore continuous random variables. Consider the following example. Suppose that your friend is throwing darts at a board that has a radius of 1 foot. Let x be the distance between their dart and the bullseye, or the center of the board represented by the red dot. And if they miss the board, they get to try again. Then x here is a random variable. Its numerical outcome varies from throw to throw, as represented by the black dots. Further, each dart has to be between 0 and 1 foot from the bullseye. That is, x must be in the interval ranging from 0 to 1. Now I want to take a quick pause here to point out something about this notation. The use of the square brackets for this interval means that x can be exactly 0, exactly 1, or anything in between. If instead we had used round brackets, it would mean that x can be between 0 and 1, but it can't be exactly 0 or exactly 1. Further, notice here that x, the distance of your friend's dart from the bullseye, is a continuous random variable. The possible outcomes of x are uncountably infinite, that is, not listable. And our ultimate goal is to understand how x varies from throw to throw. That is, we want to build a probability model that summarizes the possible outcomes of x and their relative plausibility. Now, if x were discrete, we could use a probability mass function to summarize the probability of each possible outcome of x. For example, the PMF here would summarize the probability that your friend's dart lands 0 feet, 0.1 feet, 0.2 feet, and so on from the bullseye. But since x can be any value between 0 and 1, not just in increments of 0.1, our model must describe the relative plausibility of outcomes along this entire continuum. That is, just like x itself, its model must be continuous, or at least piecewise continuous. Let's consider some general properties of a continuous probability model before applying them in our example. First, a probability model for continuous random variable x is defined by probability density function, or PDF, f of x. In particular, just as a probability mass function does for a discrete random variable, a PDF specifies the possible outcomes of x and their relative plausibilities. Further, a valid PDF satisfies the following two conditions. First, the PDF must be non-negative, that is, greater than or equal to 0. Notice then that there are no upper bounds. Mainly, unlike a discrete probability mass function, a continuous PDF can exceed 1, as is true for the example plotted here. Notice that f of x takes on values from 0 all the way up to 3. Second, across all possible values of x, the PDF must integrate to 1. In other words, the area under the PDF must be 1. The idea here is equivalent to the fact that a discrete probability mass function must sum to 1. Another difference in continuous versus discrete probability models is that we cannot interpret a continuous PDF as a probability. In fact, since PDFs can exceed 1, they definitely can't be probabilities. Rather, the PDF provides a sense of comparison. The greater the PDF at x, the greater the relative plausibility of that outcome x. Let's consider these properties in the context of our dart example. Letting x be the distance of your friend's dart from the bullseye, suppose that the variability in x can be described by PDF f of x, where f of x equals 3x squared for x between 0 and 1. This formula, in conjunction with the plot of the PDF, provides some insight into x. First, notice that the plausibility of x, as measured by f of x, increases as x increases. That is, your friend's dart is unfortunately more likely to land near the edge of the board, that is, to get a value of x near 1, than they are to get a value of x near 0, that is, for their x to be near the bullseye. Further, as an example, notice that the PDF f of x is 3 when x is 1, and the PDF is 1 when x is 0.56. Comparatively then, the plausibility of your friend hitting the edge of the board or hitting 1 foot from the bullseye is 3 times greater than them throwing a dart around 0.56 feet from the bullseye. Next, let's prove that ours is a valid PDF. First, the plot of the PDF and its formula, 3x squared, confirm that the PDF is non-negative. Second, we need to prove that the area under the PDF equals 1. To set this up, we need to integrate the PDF, 3x squared, across all possible outcomes of x between 0 and 1. Next, to simplify the integration, a good strategy is to always take any constants, here 3, outside the integral. Then the integral of x squared is 1/3 x cubed, evaluated from 0 to 1. Plugging in both 1 and 0, we have 3 times the quantity 1/3 minus 0, which simplifies to 1. Thus, we've proved that our PDF has an area of 1. It's valid. Before learning other cool things that we can do with the PDF, I want to point out 3 important components to the PDF. First, the interval from 0 to 1 is called the support of the PDF. It identifies the values for which the PDF is defined, hence the possible outcomes of random variable x. Without knowing this basic information, we really don't know anything about x. For example, we wouldn't know if the dartboard has a 1-foot radius or a 2-foot radius, or so on. Second, x squared represents the kernel of the PDF. This is essentially the piece of the PDF which depends on x. It's really the heart of the PDF. It defines the relative plausibility of the different outcomes x. The final component of this PDF is the normalizing constant, 3. This is the least important component of the PDF. The support defines the possible outcomes of x, and the kernel defines the relative plausibility of these outcomes. The role of the normalizing constant is to simply scale the PDF so that it integrates to or has an area of 1. That is, the normalizing constant ensures that the PDF is valid. In fact, if we know the kernel and we know the support, the normalizing constant, hence the complete PDF, can be identified using calculus. Meaning, really, we can define a PDF and hence a probability model without knowing the normalizing constant. This idea is related to proportionality. Since we can identify a PDF by its kernel and support, PDFs are often expressed without their normalizing constants. Specifically, a PDF is proportional to its kernel. For example, since our PDF equals 3x squared, we can drop the 3 and note that fx is proportional to x squared, where this little squiggly symbol is read as proportional to. In general, 2 functions or variables are proportional to each other if there's a constant ratio between them. For example, if x is height, or if y is height in inches, and x is height in centimeters, then y is proportional to x. Specifically, y equals 2.54x, where this ratio, 2.54, is constant. Similarly, if y is distance in kilometers and x is distance in miles, then y is proportional to x. There's a constant ratio of 0.621 between them. Finally, as a counterexample, if y is temperature in Fahrenheit and x is temperature in Celsius, then y equals 9/5 x plus 32. Thus, y is not proportional to x. Mainly the addition of 32 means that there's not a constant ratio between temperature in Fahrenheit and Celsius. Finally, let's consider some applications of a probability density function. Beyond describing the overall variability in a continuous random variable x, PDFs can be used to calculate the probability of x having an outcome within any given range a to b. Specifically, the probability that x is between a and b is the area under the PDF between these 2 points. And we can calculate this probability by integrating the PDF from A to B. Consider an example. In our dart example, what's the probability that your friend's dart falls less than 0.6 feet from the bullseye? This probability is represented by the blue shaded area at right and can be calculated by integrating the PDF from 0 to 0.6. Next, we can plug in the formula for this PDF and take the constant 3 outside the integral to simplify things. Then we can evaluate the integral 1/3 x cubed from 0 to 0.6. And plugging in these two values to a calculator, we can show that the result is 0.216. That is, there's a 21.6% chance that your friend's dart falls within 0.6 feet of the bullseye. Now, consider the extremes of these types of calculations. We showed earlier that the PDF integrates to 1 along the range of possible x values from 0 to 1. Conceptually then, there's a 100% chance or total probability that your friend's dart falls between 0 and 1 feet from the bullseye. Thus, this special case illustrates why a PDF is scaled to have an area of 1. It accounts for all possible outcomes. Consider the other extreme. Suppose we tried to calculate the probability that x equals some exact outcome A, that is, that your friend's dart falls exactly A feet from the bullseye. By definition, we could calculate this probability by integrating the PDF from A to A. But this integral, like the area of the line under the curve at A, is 0. Mainly, not only can we not interpret the PDF f of x as a probability, the probability that x can be any exact outcome is always 0. This seems a little goofy, but it does make sense in the context of a continuous random variable. Our measurements can always be more and more precise. Thus, the chance of observing any exact outcome, say your friend's dart landing 0.500001002 feet from the bullseye, is 0.